Spring scale. A student attaches a spring scale to a 0.50 kilogram container which sits on a rough surface. The student pulls horizontally on the spring scale and the container remains stationary. The student increases the applied force and the spring scale's reading continues to increase until it exceeds 3.0 newtons, at which time the container begins to move and the reading on the scale decreases. A. Find the coefficient of static friction. B. How much static friction is on the block when 1 newton, 2 newtons, and 3 newtons is applied by the student. The container is now pulled at constant speed and the student notes that the spring scale reads 2.0 newtons. C. Find the coefficient of kinetic friction. D. The student adds another 0.50 kilogram to the container. I. How does this change the kinetic friction force on the container? I. How does this change the coefficient of kinetic friction between the container and the surface? E. The spring is now pulled at constant speed but at an angle of theta above the horizontal. How will this affect the kinetic friction force on the container? And F. Make a sketch of the scale reading as a function of the applied force. Find the coefficient of static friction. First, draw a free body diagram to show the forces on the container. So what do we have? We have an applied force to the right, mg, gravity down, normal force up, and friction force opposite the direction of motion. As it takes 3.0 newtons of applied force to overcome the frictional force, the maximum force of static friction is 3.0 newtons. This can be used to calculate the coefficient of static friction. So we'll use the equality part of the static friction equation. Static friction is less than or equal to μs times normal, as we're looking for the maximum static friction. So here we have it. Here's our μs F normal. The normal force is just equal to mg because the container, is not going up and down at all. So here's our force, here's our mass, here's g, and μs is 0.61. How much static friction is on the block with 1 newton, 2 newton, and 3 newton applied by the student? We found that the maximum static friction force is 3.0 newtons. If a force equal to or smaller than 3 newtons is applied, then the static friction will exactly match the applied force. The inequality part of the equation is used. So our answer then is 1 newton, 2 newtons, and 3 newtons. Applied force is 1, you get a static friction force of 2. 2, you get 2, and finally 3, you have a static friction force of 3 newtons, which is the maximum static friction force. The container is now pulled at constant speed, or zero acceleration, and the student notes that the spring scale reads 2 newtons. Find the coefficient of kinetic friction. Since the container is moving at a constant speed, the sum of the applied force and the kinetic friction force is 0. The applied force is 2 newtons. So here is our Newton's second law equation. Once again, here's our free body diagram. So Fap minus the friction force, the kinetic friction force, equals ma, which equals 0 as it's got a constant velocity. So Fap then is equal to the friction force, which is equal to mu k times normal, which is mu k times mg. Substitute in our values, and we get mu k, the coefficient of kinetic friction, is 0.41. The coefficient of kinetic friction is less than the coefficient of static friction, which is proper. The student adds another 0.5 kilogram to the container. How does this change the kinetic friction force? And 2, or I, how does this change the coefficient of kinetic friction between the container and the surface? Well, kinetic friction force is proportional to the normal force. Therefore, as mass is added, the normal force increases, so the kinetic friction increases. Now, the coefficient of kinetic friction is constant for a specific pair of surfaces, in this case, the container and the rough surface. The mass of the container does not impact the coefficient of kinetic friction. The spring is now pulled at constant speed, but at an angle of theta above the horizontal. How will this affect the kinetic friction force on the container? Well, the kinetic friction force is dependent on the normal force. when an object is pulled upwards at an angle, the normal force is decreased. Therefore, the kinetic friction force also decreases. So here's Newton's second law. Here's our two forces in the up direction, right over here on our free body diagram. mg is pointing down. So that's really normal plus f sine theta minus mg equals 0 because it's not bouncing up and down. Switch this around, solve for the normal force. Then our frictional force is now mu k times the normal force, and here's our friction force, which, because you're subtracting this term, means the kinetic friction force decreases. Make a sketch of the scale reading as a function of the applied force. So here's our scale reading on the y-axis. Here's our applied force. When the object is not moving, the scale reading increases linearly until the static friction force cannot grow anymore. So that's this line right here. Static friction force keeps increasing until it starts moving. Then the kinetic friction force takes over and remains constant. The kinetic friction force is less than the maximum static friction force, so that's this piece here, where the scale reading gets smaller and then stays constant.